Thank you for the introduction, and good morning, everyone. So I will switch to Middle East, to another part, but still, I would say, in the tropical world. So I will talk about the benchmarking of cassava starch production systems within different countries that we implemented in the last several years, actually. I'm Guillaume Da, and I work at the University Paris-Est. And I present this work on behalf of my colleague from CIRAD, Thierry Chan. And Thierry is based in Kasset Sart University in Thailand. So, here. Just to give some few elements about cassava, because cassava is a tropical annual crop. And it's a very important crop for the tropical world, I would say. So I just point at this through the two maps that I put here to show that the cassava harvested area along the Americas, in Asia, in the Americas, in Africa, is very high, and the suitability index for this crop is also very high. So it's a very important crop for hundreds, I would say, millions of peoples, and for their livelihoods. And today, cassava is becoming important also for relatively to population growth and climate change. So one important thing is that the cassava can be processed. The cassava roots can be processed into starch. So you can see on the right part of the slide the SEM pictures taken from the roots, parenchyma in the roots, and the two products after extraction, starch on the bottom and bagasse or fibers on the top. So this is the starch that I will talk about now. Because the starch industry, of course, in these countries like Colombia, like Vietnam, Thailand, and other countries like Brazil, cassava starch industry is becoming a major industry. And what about the industry and the scale of the industry that we are talking about? So here I just defined different scales, production scales in terms of starch output. So this is a small scale, referred to as ST, is about 1 to 10 tons of starch per day per factory. And basically the process is represented here. And we can identify, I don't know if something, yeah, maybe. We can identify key operation units, so from the fresh roots to the final starch. And what we can see here is actually at small scale, what is quite typical, even if it's fairly specific to the region, is that the cassava is produced into a wet starch form before being dried. And thank you very much. Thank you. Before being dried, but sun-dried most of the time. And also that the liquid waste generated during this process is generally not treated. So it represents high levels of liquid waste discharged around the factory or the small-scale factories in general. If we look at the very large scale, which corresponds to more than 100 tons of starch per day, it's characterized by continuous processes, and it's more or less solid liquid extraction. So from the fresh roots again to the final starch, which is here, not sun-dried but flash-dried most of the time. And we can see that there's also counter-current circulation of water in the process. So there's quite a high optimization of this process at the large scale, of course. So within actually these past years, recently, from the last 10 years, I started, I think, 10 years ago, and now it's really applied in most of the time in the factories. For example, in Thailand. Thailand is the first exporter of the cassava starch in the world. So this is the treatment of the wastewater to produce energy through a biogas process. So here, the environmental issue is actually that this processing, small scale, large scale, cause significant environmental impacts, like fossil energy use or fresh water. But it also have environmental issues. It is environmental issues with regards to resource depletion and greenhouse gas emissions. So also what we can see is the implementation of clean technologies like wastewater treatment, water recycling, or biogas production, point out the adaptation of processes and transfer of technologies between countries. Because, as I mentioned, that the work that we have done here is between 3 different countries, which are very different, Vietnam, Thailand, and Colombia in the Americas. So what we looked at is the environmental diagnosis, actually, of cassava starch production, unit operation, so during the process, to identify the operation causing most impacts in terms of environmental impacts, and to assess the potential improvement through technology transfer. So we took, for that, different situations, different studies. For small scale, as I mentioned, in Vietnam or in Colombia, and for very large scale production, cassava starch production in Thailand. We cannot see here clearly, but it's about 600 to 800 tons of starch per day to process into dry starch down to, let's say, 200 tons a day. So these are the unit operation that we identify, that we actually studied separately to calculate the impact of each unit operation and to put it all together. And after we did the same for the small scale studies, and then we defined system boundaries because we used guidelines and tools from the LCA approach, life cycle assessment approach, but dedicated to this processing stage, because at the agricultural stage a lot of work have been done already. So then we take a functional unit, and the functional unit was the final start at 12% moisture. Then to assess the effect of energy use in terms of greenhouse gas emission, we use and we calculated also from interviews and calculation country-specific electricity mixes, and also we compared scenario between with or without biogas production for large-scale production. Okay, these are the scenarios that we test at this scale. So what we show here is the energy consumption per unit operation for different technologies, very large scale, small scale, with biogas or without biogas. And so what we can see is the thermal energy represented 70 to 75% of the overall energy of the process, for example, very large scale process in Thailand. And actually the biogas itself just covered 100% of the need, the energy need to dry the starch. So at very large scale, strong optimization has been done by switching from non-biogas to biogas production. At small scale, as I mentioned, drying is operated through solar drying or sun drying. And so it's relied on solar energy, and so we estimated the energy saving using this technology. Even if there's also some tests with flash dryers at small scales, but still very energy intensive processes. So the energy, actually, we can see here, this is extraction, energy used for extraction itself, energy used for rasping itself, so each unit operation. So there's some optimization to test at this scale. If we look at the fresh water use per unit operation, again here on Thailand, Vietnam, and Colombia, the 3 case studies that we used, this graph shows you the total freshwater use per process and per functional unit, so per ton of starch at 12% moisture, and by unit operation. So you can see that here, for example, compared to the two graphs at small scale, the freshwater use has been reduced through the recycling processes. So what has been done also is to try to propose and to test. It has been modelized and after tested at real scale to recycle water for small-scale production. But still, even it's a I would say engineering-wise, it's possible. But what about the adoption of this proposition, technological solution to address these problems? But it gives an optimistic result, which is reducing large volume of water discharge and creates impacts locally. Now, if we look at the greenhouse gas emission, again, for these 4 situations, we can see that the number of the diagram on the horizontal axis indicate the GHG emission per operation and total GHG emission in kilogram of CO2 equivalent per ton of starch per functional unit. So the category biogas to GHG losses to the atmosphere is represented by the category biogas, and wastewater also correspond to emission of methane from the fermentation of organic matter in the wastewater in open lagoons and waterways. So we also compared these two average electricity mixes. And so the result was not significantly very different between these two, actually, with or considering the country-specific mix or the average electricity mix. So this is my last slide. I mean, I just want to point out that in these types of studies, we complemented the LCA approach for processing stage because, as I mentioned, that cassava, of course, has been studied in terms of environmental impact at the agricultural stage for many years now. But we could actually found through this study that for technology transfer, for example, compromise can be done between electricity and water use to maximize starch recovery, for example. Also, that biogas generated from factory wastewater reduce emissions by 80%. So how about applying this technology at small scale? This is still a very big issue, I think. And also water recycling and re-engineering of some unit operation are really promising strategies. For example, the small scale that we studied in Vietnam and Colombia, the situation is very different. But in both situations, for example, just to give a little bit more details, that the small scale factories are located in the delta in Vietnam, and in Colombia it's more a mountainous area, so it also has a lot of impact of the strategy to manage water or to process starch, process cassava into starch. Okay, my presentation is finished here. Thank you for your attention.